Namaskar my dear friends. So now let us talk about output voltage regulation techniques. So in AC-DC converter basics we have already completed snubber circuit design and snubber circuits understanding. Now we'll try to understand how we can design feedback circuits so that we can do the output voltage regulation. So let us say you have designed 230 volt AC to 15 volt output DC. Okay. Now our aim would be to understand how we can keep this 15 volt output voltage regulated, or it means it should be maintained this 15 volt level, otherwise it can go little high or little low. So how you are going to make sure that a feedback circuit will be designed so that it can be made proper. Okay, so let me give you an understanding like how it works out. Okay, so let us say we have a 15 volt 1.5 ampere AC/DC converter design, and what is our aim is to design this particular 15 volt has to be, let us say this is, once it reached 15 volt it should be maintained this much, it should not go high or low, right? So how it is possible? Thing that we will be doing is we will design a voltage divider circuit using, let us say, this resistor, which is only one resistor, R3 and R5 together is only single resistor, and R7. So these two resistors 1 and 2 will be putting together, and this is the voltage, let us say Vx, or can be my V reference. So this is the V reference that will be going through TL431, and this TL431 will act as a shunt voltage regulator, which is going to help us regulate the output voltage and give the feedback through this optocoupler to the PWM controller. Okay, so our aim is to understand how we can design this particular voltage division circuit and this diode circuits or something like that. Okay, if you take some other examples, let us say I have a 12 volt 4 amperes AC/DC converter. In that also same way, these two resistors and this resistor will be designed in such a manner that output will be maintained to 12 volt. Similar to that, there are lot of other power supply designs. Let us say I have designed one power supply which is going to give us 24 volt output. Okay, so in this case you can see there are two resistors, R18 and R23. However, this feedback is taken here at the IC feedback, and there is no need of putting TL431 here, because that feedback control is actually, you know, like inbuilt inside this particular like controller IC. Okay, so there are different kinds of feedback that we use to design. However, our aim would be to design using TL431. Okay, so as you can see our aim is to go ahead and design for my switching power supply a feedback circuit using TL431, and let us try to understand how TL431 looks like and how it is going to regulate our output voltage. So TL431 will be let us say a 3-pin device which is going to be like this. It can have any other package as well. Now it will need one optocoupler to send the like voltage level signals to the primary. So the overall circuit will look like this, that there is a resistor R1 R2 which is going to act as voltage divider circuit, and this Vx will be defined as V reference, and this V reference will be making sure that this TL431, which is U1, is going to send the feedback signal or feedback voltage level to the U2, that is my optocoupler, and then it is going to go to the V error, or nothing but your feedback voltage level, right? So there are 3 steps that we have to do. One is my TL431 voltage reference, another one is choosing a optocoupler, and then designing the voltage divider circuit, which is R1 and R2, and we are going to set our Vx value to 2.495. So how does TL431 works? That we have to understand. So as you can see, TL431 is a shunt voltage regulator. This is also called as, you know, like voltage reference IC. So it has 3 pins. One is cathode, one is anode, and one is reference. Okay, you can see here they are marked as 1, 2, 3. So it is nothing but this is the reference that is set inbuilt. Okay, so this is my set value which is there inside the IC. Now my R point is going to receive a voltage divided signal from my let us say like this it is. So this is my voltage output that is there, and this R1 and R2 is going to set a voltage at pin R, and when this goes high, this will error amplifier will go on, right? I mean yeah, it will go on, and when it goes low, it will be off. So like that it will be working on, correct? So our aim is to design what are the different kinds of circuit using TL431. So let us start with first circuit. So if TL431 is acting as a programmable Zener diode, okay, so this is the only thing which is going to decide everything. Okay, so there are two lines, one is my slow line and one is my fast line. So this is called as slow lane and fast lane. You can see there is a rabbit and there is tortoise here. So that they are actually like indicating an idea of slow lane and fast lane. So this R1 and R lower will be designed to give you a voltage level here as V reference, which will be 2.495 volt, and this is how you will be giving your output through this optocoupler to V feedback. Okay, now this fast lane is actually going to have a resistor which is my pull-up resistor kind of thing. This is going to decide how much current is going to flow through the cathode of my TL431. Okay, so this R LED becomes very like important, because it is going to have a upper limit on this, like it must leave enough headroom over the TL431. So this is very critical to choose. Okay, so designing this, you can see the current that is flowing through this R LED, let us say it is current I1. So I1 value will be nothing but your 1 volt by R bias. Okay, R bias is nothing but this. Why 1 volt? Let us consider the forward voltage drop across the diode of optocoupler is close to 1 volt. So this 1 volt divided by R bias like resistance is nothing but the current that is flowing through the bias resistance. Okay, so similar to that, the current flowing through this I1 will be nothing but your V out by R LED, right? So V out by R LED will be the current flowing through this, and this is how you will be seeing the total current flowing through this TL431 is nothing but your I1. Okay, now if you see some of the formulas related to this, so the value of R LED max that we saw just now, this LED max is nothing but my output voltage minus the forward drop voltage across the diode, which is let us say 1 volt, minus voltage across TL431 minimum, which is nothing but your 2.495 volt, right, divided by my VDD minus VCE, that is your like a collector to emitter voltage, and VDD is like a primary side voltage level. Then this is my I bias into current transfer ratio. So current transfer ratio, let us say we will consider, let us say 100%. We generally choose optocoupler between, let us say 50% to 600% available optocouplers. Okay, so it means 50% CTR means current transfer ratio, means whatever the input current is there, half of that will be transferred to the output. If it is 600%, then whatever the input current is there, let us say 1 milliampere, the output current will be 600%, that is 6 times, that will be my 6 milliamperes. So like that is the understanding. Okay, so this is the this is converted into percentage, that is CTR, and R pull up and all these things you can put it, and this is how we will be finding the R LED maximum. Okay, good. Moving to the next part, let us try to understand a simple design. Okay, so let us say my output level is 5 volt. I am not taking the exact example of 15 volt. We'll take up output voltage as 5 volt. Voltage drop across the LED across the optocoupler diode is 1 volt, and TL minimum is 2.5 volt reference, that you know already, right? The VDD voltage that is there at the this one, I mean primary side, is nothing but 4.8 volt. Okay, and this collector to emitter saturation voltage is 300 millivolt. I bias that has been considered to be 1 milliampere, and current transfer ratio is considered to be 0.3, that is 30%. Okay, and pull-up resistor has been considered to be 50 kilo ohms. So pull-up resistor is which one, that you can see here. This is the pull-up resistance that is there, which is 20 kilo ohms. Okay, so in that case if you calculate R LED maximum value through the formula that was given, so it is going to be less than or equal to 857 ohm. Okay, so you have to must understand that it must be less than this. So let us say we can consider a voltage of a value for R LED is let us say 776 ohm or something. Okay, or 758 ohm or something. Okay, so basically some of the standard values that are there, even 680 ohm or something like that can be considered, but must be lower than 857 ohm. Okay, if you can see like if we increase the CTR value, my R LED maximum value will be increased. Okay, so this is how you can have a understanding here. Okay, now let us see a proper feedback circuit design that we are going to take up using TL431. So what will be the thing that we have to take care while designing the circuit is, we have these two resistors as voltage divider to generate here a voltage level of Vx, which is going to be V reference. Okay, now one more R LED that just now we calculated to limit the current through this lane. Okay, through the diode, and R bias will be the current flowing through this bias resistor. Okay, so this particular TL431 will receive a current which is flowing through this R LED. That same amount of current will be flowing through this cathode, and it must be you have to make sure that it must be greater than 1 milliampere. Okay, 1 milliamperes. Okay, then only it will get excited, otherwise it will not get excited. That's the understanding we should have. And then this pull-up resistor and VDD that is there in the primary side, that we will anywhere see that. I'm not explaining this gain, and like we have zeros and poles that is there. So if you want, you can find out where is my located zero, where is my located poles, by putting the values of C1 and C2 and R upper and R pull up. Okay, so R pull up and R upper is there. Where is my upper? There is R upper, here it was. So R lower and R upper is basically this one, which is considered as R upper. That's the reason it is told. Okay, now let us talk about another method of removing the fast lane. So what happens is, if you could remove this fast lane understanding or fast lane circuit, then you can have a a good understanding of how to develop a proper feedback circuit. So this can be designed using a fixed bias method. So fixed bias method, how do you put fixed biasing? So fixed biasing is nothing but it will be clamped to a particular voltage level. Okay, so that is nothing but it can be done by using a Zener diode. Okay, so just cut this line and you are going to insert a Zener diode here. So this is what is done here. So a Zener diode, let us say if it is 5 volt, then we can put it like, let us say we are going to fix it to 6.2 volt or something. So it must not increase more than that. Okay, so this Zener diode will help you to have a fixed bias, and this is how you will be getting rid of your fast lane lines. Okay, and one more thing that will be inserted is one additional 0 will be inserted by putting this RC value. So this C1 and R2 will be inserted, and this is how you will be having a proper feedback circuit design using this. Okay, so let's see a calculation with this one. So if you see a calculation, what we are going to see is no fast lane, means fast lane we have suppressed by using a Zener diode. Okay, so in that case what will happen is my R LED maximum will be equal to this value, this formula, right? So VZ, earlier we had put it V input. Okay, so that was 15 volt or like 5 volt or something. Now it will be put VZ. Just now I told you this was V out. Now it has been converted to VZ because the fixed bias has been applied. So if you see a particular like application that is shown here by the application note. VZ is 6.2 volt, VF is 1 volt, VTL is 2.5, and VDD is same, all these things. So in this case you are going to see my R LED is less than equal to 1.5 kilo ohm. Okay, and if you have once you are selecting a particular resistance value, you must give 15% of margin. So give a little bit lower value, so it is 1.27 kilo ohm. If you want, you can choose let us say 1 kilo ohm resistor. That is more than enough for your design. Okay, let us see another one. So if you want to have more calculation in this, you can calculate what is the extra gain term. So that is nothing but your R pull up by R LED into current transfer ratio. So that is going to give you 4.72 gain, and the total gain that will be required is going to be how much? The required total midband attenuation at 1.4 kilohertz is, let us say, minus 10 dB. So in that case, G FC will be 10 to the power minus 10 by 20. Like gain in dB is nothing but 10 log gain. Okay, let us say x is my gain, so 10 log n. So if you want to have value of x, it is nothing but 10 to the power what will happen, gain or G dB divided by 10. So this is what it is, sorry, it is 20 log 10, so it is 20 log x. So G dB is minus 10, so minus 10 by 20. This is how you have got this particular formula. Okay, so gain in dB is nothing but 20 log x, and if it is to be minus 10 dB, so this will be 10 to the power G dB by 20, and G dB is minus 10. That's the reason you have got this value, right? Now if you see other forms, so if you want, you can calculate all these things, and R1, R2, all these values will be calculated. Anyway, I will proceed next. So what we'll do is, there are another type of feedback like circuit design, which is called as type 3, but it is bit difficult to put into practice. Okay, so basically what will happen is, across this LED, I mean R LED, we are going to put RC circuit, and designing this is becomes little bit tedious task. Okay, that's the reason we'll not take this into account. However, this can also be like designed like this. If you want, you can put your like what is your zeros frequencies and pole frequencies. If you want, you can calculate, and where your zeros and poles are lying in your system response. Okay, so at last you will see a very nice and like a complicated output circuit will be with removing of fast lane. You are going to have Zener diode here, then insertion of this like RC circuit, and then insertion of this R3C3 as well. So this becomes little bit difficult to calculate all these values. So what we will do is, we'll try to follow the very simple one which we had seen in the first, just R1 and R lower, and with R bias and one capacitor and R LED. That's all. So with this we will be able to design our complete feedback circuit using our optocoupler and TL431. Okay, so the complex thing we will not try to get into now. Unless we understand the TL431, it's not like complete. So what we'll do is, we'll take few things from TL431 datasheet and try to understand what are the information that we need to take into account. Okay, so once we open the TL431 datasheet, what we see is, see, this is my TL431 datasheet that is there from Texas Instrument. Okay, so I have taken it from Texas Instrument, which is there TL431 or TL432, and this is also called as precision programmable reference. Okay, so it can be used in your like a AC inverter or industrial AC DC converter. So you can see AC DC converter, it can be utilized, and that's the reason I have taken this particular TL431. So by default, or like blindly, you can utilize TL431 in your feedback circuit design for your AC DC converter, because TL431 can be considered as it is the law in AC DC converter. Okay, so some of the things that I want to show it to you is, let us talk about a recommended operating condition for TL431. So what is the cathode voltage that will be there is V reference to 36 volt. It means your V output must be less than 36 volt. Okay, otherwise it will not be able to regulate, or it will not be able to give you a feedback regulation circuits. Okay, so either you can design a AC-DC converter with 5 volt output, or let's say 7 volt output, or 10 volt output, or 12 volt output, whatever voltage output, but it must be less than 36 volt. Okay, so up to 30 volt, I think I recommend you to go ahead up to 30 volt with this method to design your output voltage. Okay, the cathode current that must be between 1 milliampere to 100 milliampere. That's the reason I told you keep minimum 1 milliampere current, otherwise the TL431 will not get excited and it will not give you the feedback values. The operating temperature is 3 operating temperatures are there: 0 to 70 degree, minus 40 to 85, and minus 40 to 125 degree centigrade. So whichever like temperature range you want to utilize, you can use. If you want to utilize for industrial temperature range, go ahead with minus 40 to 85 degree. That is actually better. If you want to have some extended temperature range, you can go ahead with 125 degree centigrade. And for consumer applications and all, you can go ahead with this one, which will be the lowest cost, which is 0 to 70 degree centigrade. Some more electrical characteristics, if you see, we have like voltage reference, which is nothing but 2495 millivolt, that is nothing but 2.495 millivolts. Then we have V reference, that is just plus minus 1 millivolt range. So this is how that is there. Now if you talk about minimum cathode current required for regulation is 0.4 milliampere, okay, or 400 microamperes. Okay, so you have to understand the cathode current that is coming into the cathode of TL431 must be more than this, otherwise it will be tough, otherwise it will not get excited and you will not see the output properly. Okay, now let us see some of the circuits that is given in the data sheet itself. So how to design circuits with TL431, you can see. Let us say you want to have VK is equal to 2.5 volt. Okay, so you can see you just give your V input. This is my V input. One resistor will be there which will be actually limiting the current through the cathode of this particular TL431. Okay, and my V output, which is going to be VKA, that is going to be my equal to V reference, which is your 2.5 volt. Okay, so this is how very simply you can just tie your cathode and reference value. This is my cathode point, this is my reference point, and this is my anode point. Okay, so if you tie together reference and cathode, you will get your Ka as 2.5 volt output. So whatever the input is there, if you want to regulate to 2.5 volt at output, you can put a current limiting resistor, and that is more than enough. Okay, now let us say you want to design a separate output voltage, which is going to be my Vk, that is nothing but your V output. So let us see if it has to be 15 volt or 20 volt or 12 volt. So basically you have to design your Vx, which is going to be 2.5 volt using your R1 and R2, and this will determine my VKA. So put your R1 and R2, and using this you are going to design your VKA value, that is nothing but your output value. So this is what the formula we will be utilizing. In simple term, we will be discarding this I reference into R1 because this is very insignificant, because I reference is nothing but the current flowing through in the reference pin, which is in microamperes. Okay, so the value of this will be very insignificant. So this is the normal formula that we will be using, which is V reference into 1 plus R1 by R2. Okay, I'll show you the power of this particular TL431 circuit by taking some of the application circuits. So you can see, if you want to have 5 volt regulator, okay, 5 volt regulator, so what you can do is you can use one 5 volt regulator simply and give your take your output as V out as 5 volt. However, TL431 makes sure that it gives you a proper or very precise value of your output voltage. How? You can have this one as R1 and R2, and you are going to design. So let us say 5 volt it has to be, so it will be like 2.5 volt. So both the resistors are same, you can see, right? And this is how it has generated a reference and given you the feedback to maintain the output voltage to be 5 volt. Okay, and this resistor has been used just to limit the current through the cathode of this particular TL431. Okay, so this R is equal to 8.2 kilo ohm has been used to regulate or to limit the current through the cathode of this IC. Similar to that, one more regulator is there, which is, let us say, 5 volt precision regulator I want to make. So if you do not want to utilize a regulator or something, you just choose one transistor which is capable of supplying that much current. Okay, and what is the understanding that we have? Let us say 5 volt is needed, so half of like 2.5 volt we have to generate here. So you can see R1 and R2 both are same value with 2.5 volt generated here at V reference, and this is how you are going to make output as 5 volt. And similar to that, you have to make sure like what is the RB value that should be there. It must so that the current flowing through this particular cathode must be greater than 1 milliamperes. Okay, so if my V input is, let us say, 12 volt and 12 volt to 5 volt, so your understanding should be my RB must be less than 12 kilo ohm. Let us say 10 kilo ohm will be a good idea. Okay, or 8.2 kilo ohm itself from this one you can take it here. Okay, so the very important thing that comes up is which of this part, like TL431 has several parts. Okay, like it has so many packages, so many parts, and so many temperature ranges, all these things. So which part we should consider? So it here comes or part ordering information. Okay, so from this part ordering information you will be able to find out, like let us say we have the part TL431. So TL431. Now what is the accuracy that you want, whether you want 0.5% or 1%, or if you want blank, that is 2%. So if you want to have little bit, let's say middle one, so I will take it as A. Okay, then operating temperature range, so this is operating temperature range like CIQ. So let us say I want it I, which is going to be minus 40 to 85 degrees centigrade. Similar to that, this 3 digit is going to define your package type, like SC70 package or SOIC package or PDIP package or SOT89 package. All these things are there. So SOT89 package will be like very good one, or PDIP package will be very good one, like a sturdy packages. SOT packages will be little bit lower capabilities. Okay, TO92 package will also be very costly, and it has a maximum amount of heat dissipation capabilities. Okay, so what we will do is, for our understanding, we will take the lowest one, which is going to be this one, T23-3. So that is going to be DBZ. Okay, so this is the lowest cost that I will take it. Now package quantity, if you want, you can have like tape or reel or something. So later you don't have to worry about. So this is my part number that can be utilized very easily. If you want TO92 package, what I will do is I can have TL431 AI, and then at last I will have LP. Okay, so this is how you will be using. Sometimes people prefer PD package, so just you write down at after AI just put P. So this is another part for PD package. So this is going to be my SOT23-3, then this is going to be TO92, and then let us say TL431 AIP, that is going to be my PD package. Okay, good. So these are the 3 parts that you can utilize. So at last what I will do is, since our aim was to design the feedback circuit for this particular session, so we will take up this particular circuit as a reference, and the same manner we will try to have our feedback circuit design. So I will take one R1 here, and then this can be my R2 kind of thing. Okay, we will have one R bias resistor and C1, and then a lead resistor which will limit the current through this cathode. Okay, and this is my optocoupler which will be sending the feedback voltage to the primary of the circuit, or it is to my PWM controller. Okay, so hope now you have a very good idea of how to deal with TL431 to design your feedback circuit to regulate your output voltage of your AC-DC converter design. So alright, With this, what we'll do is we'll directly jump into the AC/DC converter design from our next session. So as you can see, we have our first AC/DC converter that is going to be in our design processes, 15 volt 1.5 ampere rating, using one of the IC. So we'll try to understand a basic idea of how to design one by one each of the sections. Thank you guys.